Hey there guys, Will here. Today let's investigate the noise level in Cloud Commons area. The slide is made by William Zong, submitted on the 16th of this month at the Georgia Institute of Technology. Let's begin. So why the COLC, or Cloud Undergraduate Learning Commons? In the weekday noise level during its peak evening time, it may distract learning for individual students, peak being defined by many students coming in through these kinds of floors and levels. So this study compares the data of noise in these learning areas versus a quiet room to help determine its relative performance for a quiet time. Since, it's a library, and libraries generally have quiet times. So, for the setup for the COLC, we put it into the second level of the COLC, where inside of the second level, we're going to go ahead and use MyDAC hardware and MyDAC microphone to record the noise level. The data is collected between the times of 1:20 and 2 p.m., which is close to the peak hours of students that come through this level of the COLC, and of course, being a little bit loud as they transition from class to class. The microphone is first calibrated at our first setup wave in time, where we use about 2.5 volts that was recorded at this kind of more quiet relative time to compare against. For the software, I'm using GaTech AE, which is used to read and parse data from the MyDAC, and it's recorded into text files for graphing purposes for later experiment. Same for the Lab 3, where we also use GaTech, a MyDAC, and its accompanying microphone. Only difference now is that we also have a headphone jack module to detect voltage changes in the audio. In sequential order, we'll be playing files of audio sine waves in varying hertz, ranging from 20 Hz to 10,000 Hz. The microphone is placed around 3 to 6 centimeters away from the speakers of the laptop that's being measured. And for the headphone jack, we're just going to record the sine waves through the laptop head jack and the voltages that they display from there. So let's start off with Lab 3 then. Lab 3 says that for the top graph and the top right is our headphone graph, and our microphone graph in the bottom right is shown when it plays a 5 kHz sine. The headphone has less power densities needed at our 5 kHz line, and we see this with the little text box that's put at each of the peaks of the graph. But for the same around 5 kHz, we see that the headphone requires 0.07 and the mic requires 0.4. Now, they share both of the same peaks, so that's good. However, although both were taken at the 235th sample of 1024 samples taken, we could also see that all of these observed behaviors are similar to all waves for both the headphone and microphone jack for their respective samples. So let's look at that right quick. Both demonstrated downwards incremental changes in the power spectrum for increased frequencies. And we could see that over here, where generally all of our peaks align, like so, as you guys could see between these two. And we also see that for the same given hertz, there's going to be less power density for the headphone. Relative response. By dividing each tone of the frequency by the power at the same tone frequency required from a direct connection, we could see that our graph seems to be an exponential decay. So this kind of tells us that our relative response will drop off at higher hertz. And the discussion of the COLC results is that our noise level is evenly spread across all the samples, given that we don't have a peak. So for example, in our previous 5 kHz example, we see that we have some kind of peak frequency to locate, but here inside of the COLC, we see that the noise is generally evenly distributed across all samples. So we could say that's a Gaussian noise. So the usual value is around 4.5 to 5.1 volts across all the sampling periods of this 30 seconds. So if I quickly go here and play it, you kind of see that as I scroll through this, that generally, yes, it will be between 4.5 and 5.1 volts, although most nominally it will most likely be near 4.5 volts. But yes, it does fluctuate sometimes to 5.1. So some conclusions to draw is that increasing the frequencies for lab 3 would hold less power spectrum for the same sound wave of sound emitted from a transmitter signal. And headphones generally require less power than the microphones, and the relative response of a MyDAC microphone is exponential decay for higher frequencies. For the Kolk operation lab, we see that compared to an initial 2.5 volt reading when setting up in a relatively quiet room, the Kolk is comparatively distracting. It can be modeled as a Gaussian noise, which is random interleaved acoustic waves. We could say that the second floor is therefore relatively very noisy and cannot be used for quiet times. That is all. Y'all have a beautiful day.